Here's a table that's going to be helpful for some of the problems that you're going to be doing. Here's the list of some different solvents, their respective boiling points and freezing points, which will be helpful for if you have to find the new boiling point, the new freezing point. And then these are the KB and the KF values that will have to be used in the freezing point, depression, and the boiling point elevation equations. Okay, again, we're looking for what that is for the solvent. So let's see how we can utilize that equation. Here, we're making a solution by dissolving some glucose in water. And it says here that the resulting boiling point after having dissolved at 18 grams in that water is 100.34. Now we know pure water boils at 100 degrees at 1 atmosphere pressure, and so by adding that little bit of glucose, we've actually increased the boiling point really only 0.34 degrees, but still it has been increased. So from this information, they want you to calculate the molar mass of glucose. What you want to remember, and I mentioned this before, whenever you're looking for molar mass, that is always grams divided by moles. And that would be of your solute in this case. So looking at your equation, your solute's glucose, do we have either grams or moles of the glucose? Well, sure we do. We've got the 18 grams, so we have our numerator. It doesn't say anything in here about moles, so we need to hunt down the moles, and then we'll be able to divide the two, get the molar mass. Keeping in mind that it says we have a new boiling point, so this is talking about boiling point elevation. We're going to look at this number and recognize that from this and knowing the boiling point of pure water, we can find that boiling point elevation, and that means we can utilize this equation right here. All right. Now, in this equation right here is hidden moles. Okay, where do you think moles are hidden in that equation? Well, K is a constant, T is just a temperature change, but we know we've got molality here. All right, and from that molality, we can find moles because molality is moles per kilogram. So somehow we're going to dig the moles out of this. Well, what do we have? We've got the change in temperature. This is not the change in temperature. This is the new boiling point. We know the original boiling point is 100, so we simply subtract the 2, and that gives us our change in boiling point. Now, this number right here, it would be called the boiling point elevation. This would be our new boiling point. This is the boiling point elevation. Again, like I talked about with vapor pressure, be careful of the wording. What do they want you to find? Okay, sometimes they might want to know the boiling point elevation. Sometimes they might want to know the new boiling point, so keep that in mind. Okay, back to what we were doing. So we can plug in this for the delta T. K sub B, you go back to that previous chart I was telling you, and you look up the K sub B value for water. Okay, and that happens to be this 0.51 degrees Celsius kilogram per mole, and that is in there, that unit is in there because of our molality unit. All right, and we're going to plug those numbers in, the 0.34 in here, put that KB value in, and we're going to solve for molality, and that's what they've done here. Okay, they've just rearranged the equation, and here's our molality. And now that we know molality, what we can do, this is how I like to do it. If I've got little m, then I've got moles over kilograms, right? Okay, so I just found little m, so this is going to go right here. All right. Kilograms, remember this is the mass of the solvent. Well, my solvent's water. I have 150 grams of it. I can convert that to kilograms and that'll be my denominator. And then, hey, look, there's the moles I was looking for because this is moles of solute, which is the glucose. So once I figure out by plugging in the molality, the 0.1500 kilograms in here, I can solve for moles. And that's what's happening down here in this setup. Okay, they plugged all that into the equation. They do it a little bit different. This is the equation I like to work with. And I find out that I have 0.1 moles of glucose. Now we have to keep in mind here, what is my solute? My solute is a covalent compound. So for every one glucose molecule I place in the solution, I get one glucose molecule. It doesn't dissociate. So if I have 0.1 moles of glucose in the solution, then I have 0.1 moles of particles in the solution. So this is the value that I will plug in here to find my molar mass down here in the denominator. And so you would simply put the 18 grams from here into the numerator, right there, and then the 0.1 moles are going to go in the denominator in the moles, and then we have our grams per mole, which is our molar mass, and it ends up being 180 grams per mole. You could double check by looking that up, but that's one application of boiling point elevation, as I had mentioned earlier. Again, we might simply be plugging and chugging and solving for the boiling point elevation, and then wanting to know what the new boiling point is. Keep in mind, if you are hunting delta T and we want to know the new boiling point, you have to take the delta T and add it to the original boiling point of the solvent. We did this last year, so I don't really want to spend a lot of time on that, but keep that in mind. If you are looking for delta T, that would be your boiling point elevation. Add it to the original boiling point of the solvent. Okay, a little picture of making candy, which is the idea is by adding that sugar in there, you increase the temperature of the water and it can get really hot and yummy when it's all done. Anyway, okay, so freezing point depression is the third of the colligative properties, and you will see that it looks very much like boiling point elevation. A couple of differences about freezing point depression is it does lower the freezing point of the pure solvent by adding a solute. You dissolve that solute, the freezing point lowers. And the basic idea is, again, vapor pressure. Something freezes when the vapor pressure of the liquid matches the vapor pressure of the solid, and that whatever temperature that happens, then it will freeze. So if you make a solution, what has happened is by making that solution, you have lowered the vapor pressure of that solution, which means to get that to match the vapor pressure of the pure solvent, in a solid, you're going to have to really lower the pressure of that, or I'm sorry, lower the temperature of that solid or of that solution to get the vapor pressure of the solution to actually match the vapor pressure of the solid. And then at that point, that will be your freezing point. Again, also another interaction is those intermolecular forces that are kind of inhibiting crystal formation as well. I think in your note packet I put a couple of extra pages that kind of display this to you with some different beakers. I can't remember if it's freezing point or if it's boiling point elevation, but kind of gives you an idea of what's happening at the molecular level, so make sure you take a look at that. Here's your equation for freezing point depression. Looks just like boiling point elevation. The only difference here is this has K sub F, which is the Molal freezing point depression constant. And those are different than the KB values, but they are specific to the solvent, just like the KB is. So this equation works very much the same as the other. So the only other thing that you might want to keep in mind is if you do find delta T and you want to find the new freezing point, then you're going to subtract the change in temperature or the freezing point depression, which is what this is called, from the original freezing point of the solvent, because again, you're lowering it. So subtraction when you're doing freezing point, you add that change in temperature if you're doing boiling. So another example here, we want to know what's it asking for? What is the mass of ethylene glycol, which look at that, that's a covalent compound in antifreeze, and you have 10 liters of water, and it's going to produce a freezing point of -10 degrees Fahrenheit, which is actually -23.3 Celsius. So water originally freezes at 0. Its freezing point depression is going to be 23.3 degrees Celsius, and then this is the new freezing point. And they tell us the density of the water. And so we want to find the mass of that that ethylene glycol that was dissolved in there. So it's really just plugging in the values into your freezing point depression equation, and then our mass is going to be located in by finding the moles of the solute that was present, and then we can convert that to grams. So that's kind of what's going to happen here. So we're rearranging this equation looking for molality, because hidden in molality are the moles of the substance, and then once we have the moles of the solute, then we can convert to grams because we know what the molar mass is. So here's our freezing point depression. based on what I mentioned before. Our KF value, go back to that table there and look at our solvent is water. So we look at the KF value for water, and then plugging that in gives us 12.5 moles per kilogram as our molality. And doing like we did on the previous problem, plugging molality in, then we're hunting moles. We have the mass, actually we don't have the mass of our solvent, but we can find it very easily. 10 liters of water at 1 gram per milliliter, that will convert us to grams. And that is not done down here, but here they've just told us that 10 liters is 10 kilograms. So that is plugged into our molality equation, and we solve for the moles of the ethylene glycol, and then we're going moles to grams here to determine how much has to be dissolved to cause that to happen. So it ends up about 7.76 kilograms of ethylene glycol must be added to get this effect here. And that is another application of freezing point depression, is antifreeze. And what that does is that, again, extends the range at which that particular liquid is, a particular substance is a liquid. So you can go much lower in its temperature before it freezes, and then much higher in its temperature before it boils. And that's the purpose of antifreeze, is to keep your engine from locking up when it's really cold, or by getting too hot when the weather's warm. Okay, so then a couple pictures, you can look at those. We talked about the salt in the road and the antifreeze, that kind of thing. Okay, and then here's just another example of determining the molar mass using freezing point depression. This is very similar to the previous example with the boiling point elevation. And so you can take a look at this problem here. I don't think I'm going to go over it. The one thing that I do want to talk about, which I guess I'll have to wait a little bit, is a modification of the boiling point elevation and freezing point depression equation. There's one variable, it's not a variable, but one component that is not included yet, and I'll have to talk about that when I get back, and that's the dissolution of the particles, the dissociation versus it being covalent. So we'll talk about that later. Okay, so let me figure out what your homework's going to be. In fact, maybe what I'll just do is I'll post that on Canvas so you know which problems to do that correspond to these sections we've talked about. So sorry to bore you to death, everybody, and about all the interruptions, and hopefully you caught both videos. And hey, have a good weekend, and see you later.